All right, so for the golden ratio, yeah, it's actually interesting, and he mentions this. You basically have to start from the definition of the golden ratio, and I'm not sure if you guys know that definition. I probably haven't drawn this quite right, but what is the definition of the golden ratio? Do you know?
I think it's 1 plus root 5 over 2.
Right, that's what the golden ratio equals. That's the number for the ratio. Actually, yeah, I think that's right. But what's the definition of the ratio?
So I think isn't it x to 1 equals x 1 minus x to x, something like that.
Okay, so what the definition is, and if we call this x and this 1, what we're trying to solve for is if we take out a square here, of side length 1, that this ratio here, for this rectangle, and you remember what word this ratio was called? Or phrase? He mentioned it a few times in the video.
The golden rectangle ratio?
Yeah, it was called the aspect ratio. The long side to the short side. So x to 1 equals, well, how long is this side now?
So that's 1, it's the 5 minus 1.
Okay, so this is x minus 1. So x, the long side to the short side, is x to 1 equals here, the long side to the short side. 1 over x minus 1. So the ratio of the long side to the short side, x to 1, equals the ratio of the long side to the short side, 1 to x minus 1, right away. So that's the definition of the golden ratio.
Alright.
And how would I solve an equation like this? Do you know?
Well, you could multiply by x minus 1 just to get rid of the fractions.
Yeah. So in order to do it on our whiteboard, let's get rid of the rectangle for a second. So x over 1 equals 1 over x minus 1. This tells me that x times x minus 1 equals 1.
Mm-hmm.
And how does that simplify?
So you get x squared minus x.
Okay, do you know how to solve equations like this? Have you seen this before?
Not a super lot.
Okay. How about you? What do you do here?
So you move the 1 to the other side and say x squared minus x minus 1 equals 0.
Alright.
And then from here, we can use the quadratic formula to solve this.
Okay. And the quadratic formula tells us that the solutions, that there are going to be two solutions to this equation.
Mm-hmm.
And what are they?
So it's going to be minus 1, or plus 1, sorry.
Minus the
Yeah,
square.
minus 1.
1
Plus or minus
plus or minus.
the square root of 1, and then plus 4, square root of 5, over 2.
Over 2. Okay, now what is the square root of 5 as a number? Do you know what it is approximately?
It's a little above 2.
It's a little above 2. So I have one positive solution here for x and one negative solution for x. And what was the side of our rectangle? Was it 1 plus root 5 over 2 or 1 minus?
Plus root 5 over 2.
1 plus root 5 over 2.
Since we need it's a distance, so it needs to be positive.
Okay. So that's how we find, that's how we solve this equation. And what else did you think was interesting about this?
I thought the actual the spiral of the golden ratio.
Oh, the spiral of the golden ratio was neat. Okay. Yeah. So if we have, and here I will have to draw it accurately, but I will not be able to draw it accurately. So if I have a square cut out, and then I have a similar rectangle here, which it doesn't look like I do, but the square cut out, and then I guess I would have to be going this way, it's spiraling in like that, right?
Yep.
And I would have to keep getting similar rectangles all the way through.
Yep.
and it's just one square, then one square, then one square, then one square. It is pretty neat. What did you think was neat about that?
That it's the only spiral that only uses one square of each type.
Yeah. Yeah. Well, that's actually a good question. Why? How do we know it's the only one?
Well, anything else, and then, so like, if this was off slightly, you'd still be able to use this square. This square would have to be longer and then out, protruding more, so that would it just starts throwing off the pattern.
Okay. What do you think? Why do you think it's the only one that uses one square every time?
Well, you can look from the continued fraction approach from this, and then you know that there's only one continued fraction that can use all ones,
Okay.
and that's what we have here.
Okay. Interesting. All right. Well, let's go now and see if we can use his idea about root 2 to prove the root 2 is irrational. Okay.
All right.